Okay, let's have an example to use Taylor series as an approximation for a polynomial. You can see we have a polynomial over here, and we want to use from 0 to 4th order Taylor series to approximate this function. And the initial will start from 0, and the step size is 1. We can define these by ourselves if the question doesn't give them. And we want to predict the function value at xi plus 1 equals 1. So when x is 1, we want to predict the result. But here, because we know the exact function, we easily can find the exact results. Let's start finding the exact results. Actually, we know the function, so we can find exact results. So if x is 0, f0 is simply from this equation above. From this, we will just calculate for 0. You can see that all the terms are 0 and it's just 1.2. So the result is 1.2. If we continue, x is, let's make this from 0 to 1 up to 1, some iterative procedure. We can have some different step sizes to be able to plot a curve of this. So we want to plot the curve of this from 0 to 1 for x, and that's why we will use some middle values. I decided to use just 4 division, 0.25, 0.5, 0.75. If you want to use an Excel or MATLAB, you can increase the values to have the exact curve, trend, let's say. But for demonstrative purposes, this should be enough. So for this, f 0.25 is equivalent to, if we write x 0.25 to the function, it will give us 1.1035. For this one, f 0.5 is equivalent to 0.925. For this one, f 0.75 is equivalent to 0.6363, and for this one finally, f1 is equivalent to 0.2. So these are the exact values, and maybe for these exact values we can plot the figure and see how the curve behave. And in here I will just plot a function curve fx to x. So if we plot these, let's plot them with 0, 0.25, 0.5, 0.75, and 1. And for 0, the value was 1.2. We can say maybe this is 1.2, 1.2, and this is the value. For 0.25, it's 1.1, almost, very close to this one, 1035. For 0.5, it is 0.925. Let's have some gap between these. Maybe this can be kind of 0.925. Then for 0.75, it is 6363, point, maybe this one, 63, 63. Here. Also for finally 1, it is 0.2, 0.2. Maybe here. And when we combine these, we will have a general trend of function between 1 and 1 and 0. Of course, we can increase the numbers, x values, to above 1 and below 0. But this is just this part, demonstration of this part. So this is basically a parabola like this. If I can go through all the values. Of course, there is not small oscillations. It's just a smooth, but I wasn't able to draw like that. Assume that this is a smooth parabola. So for this one, now what we want to do is to be able to use Taylor series. We can start with the 0 order. Let's start with n equals 0. That means 0 order. Taylor series or expansion. And we know that this is the approximation of xi plus 1 is just equivalent to the current value of function at x. And for that purpose, we just say we need to define xi, and the question says xi is 0, xi equals 0 at the beginning, and h is 1. But h is not important for 0 order, but the further orders it's important. Here it's just, and xi plus 1 is 1, so this is 1, this is 0 actually. f1 is equivalent to f0, meaning f0 is, so this is the exact value. This is the approximation value. If this is exact value, we can just use the exact value result, 1.2 over here, which means 1.2. Simply we define f1 as 1.2, but in exact solution, you can see f1 is 0.2. So it's very far away. So we make a bad prediction over here. And if we calculate the error between them, the truncation error between the true value and the approximation value, this is true value minus approximation value 1.2. The error is -1. So it's too much. Graphically, we can show this as, so this is x and this is fx. For x, if x is 1, fx is 1.2, meaning that 1.2 is at 1. So we will kind of have a function like this for 0 order approximation. So this is very bad approximation. You can see we have a parabola which is shown by blue, and we are approximating it with a constant line which is shown by red. So this is very bad approximation. And to be able to improve the accuracy, we need to add terms so that we can get closer to the parabola. And let's do them in the other slide, because we are out of space here. Maybe we can add the second one, then continue to the other one. N equals 1. Let me write it here with, again, black color maybe. Here n equals 0, here n equals 1. First order Taylor series. And for first order Taylor series, we know that it is a little bit long. Let me write down like this. F xi plus 1 prediction is equivalent to fxi plus the derivative of xi and the step size h. So it is the difference between actually xi plus 1 minus xi. And the question is already saying that we need to use h equals 1, so that's easy. We could have used the different step sizes. You can check that for investigating the accuracy effect of h value to the accuracy. But for now we will consider h is 1. So this is 1. And xi is 0 again. Xi is 0 and this is 1. And here we know this real value of this, which is f0 is 1.2 from here again. And we don't know the derivative. So let's calculate the derivative. To calculate the derivative, we need the exact function, the derivative of this. Then, because this is exact function, there is no tilde on top of it. If there is tilde, this is approximation. If there is no tilde, it's the exact or true function. So fx is equivalent, if we take the derivative of these, minus 0.4 x3 minus 0.45 x2 minus 0. Sorry, that's 2 minus 1, or just minus x square minus 0.25. And if x is 0, then if we calculate this, fx equals minus 0.25. Now we can write this fx value to the approximation, first order approximation, and then we can get the fx value as f1 is equivalent to 1.2 here plus 0.25, which is minus actually, then minus 0.25 times 1, and it gives us the value of 0.95. And the resulting error for this ET is equivalent to the actual value is 0.2 always here, and we subtract the estimated value 0.95. You can see actually from here to here, this was the first approximation for 0 order. This is the approximation for first order. 1.2 to 95, it is decreasing. So it will decrease further if we increase the order, let's say. And the error here is smaller, that's why. And the value of the error is 0.75. And if we want to plot this to the graph, you can see on the graph that we will have, let me draw with green for this time, or maybe orange. We will have the value 95, which is somewhere here. And again for the value of 1. And the initial value is 1.2. So from here to here, this is a first order function, that's why it's linear, just linear trend like this. But it is getting closer to the blue parabola. It's still very far away. We need to further increase the degree according to these. And let's increase the degree to 2 and 4, 2 and 3 and 4. It says up to 4 in the following slide. In this slide, I put the figure again to the left side to be able to draw the further increased orders, predictions. And now we finished n equals 0 and n equals 1. This is n equals 1, fx prediction, fxi plus 1, or fx doesn't matter, actually the continuous function is fx. So now we will continue with n equals 2. N equals 2, meaning second order. In the second order, we will have, let me write directly the values. Xi plus 1 is equivalent to, as the prediction, to the exact value of xi, which is 0, f0, plus f derivative 0 times h, which is 1, plus f second derivative 0 divided by 2 factorial times h. And here h is 1. H is 1. We just need the second derivative of the exact function. And that's, if we take the derivative again, in the previous slide we took the first derivative, now the second derivative from there, 1.2x squared minus 0.9x minus x. And from here, if x is 0, the derivative is 0. Then this means we will put 0 here. Sorry, not here. This was not 0. This is the first derivative. This is the second derivative. This is 0. Then the second term becomes 0 actually. And the first derivative was, if you remember, this is 0.25 and minus. And the exact 0 value was 1.2. If we calculate this using these values, f1 is equivalent to 1.2 minus 0.25 times 1 plus 0.0 divided by 2 times 1 square. And from here, we will have 0.45. Here, actually, this derivative is 1. So that's why this is not 0, this is not 0. If it is 1, and if we put 0 for all the x's, it becomes actually only minus 1. So this is minus 1 here. And the result here is minus 45. So we calculated the second derivative as minus 1 because this was 1, and the approximation with the second order Tyler was minus 45. So we can simply calculate ET is equivalent to 0.2 minus 0.45, so minus 0.45. Sorry, like this, is equivalent to minus 0.25. So this is the mistake actually. This is 0.45 only. That's why it's minus 0.25. You can see that the error reduced, and also the prediction value reduced and got closer to 0.2. And if we want to plot this, of course, while plotting, we need to plot between 0 and 1 some values as well. But for now, we know that second order is a parabola. That's why we can just plot the last term. Let's use green. Last term for 1, it is 0.45, somewhere here. For 1, the value is here, from 1.240. This is kind of a parabola like this. So it is getting closer to our curve when we increase the value. And this is n equals to fx prediction. And adding additional terms will improve the prediction more. Let's say for n equals 3. N equals 3. You can solve this. I will not solve. But I want to show the derivative actually only. Fx, if we say f3x is needed for n equals 3, and it is, if we take the derivative of this, minus 2.4x minus 0.9. And here, if we say x, the derivative is 0.9. And n equals 4, let's say the final is this actually. We wanted to have up to this point. And our fx is fx I plus 1 is equivalent to, for this one, simply let me write just the values, 1.2 again, minus the first order terms the values of them was 0.25 times H1 minus the second order term 0.45 times 1 square. By the way, this is square. It has to be square over here. And for the third term, it is here actually F1 becomes minus 0.15. So here 0.15. You can solve for this entry. I will keep it short. 1 square, 1 cube minus 0.1 times 1/4 H4. So this is not actually this value. Let's remove this because there is a factorial under it. 3 factorial. The value divided by 3 factorial is this value. You can check that. And 0.1 is similar. The derivative divided by the 4 factorial is this value. Then finally the result from here, I want to keep it short, plus 1 equals 0.2. If you remember, our exact value was for 1, 0.2. And here we got the exact value. And actually this xi plus 1, we solved it for value 1 actually. Let me write 1. So this is exactly the exact value. So how could we get the exact value from an approximation? And the answer is easy. We mentioned earlier that a Taylor series with a certain order is an exact solution for a polynomial with the same order. So because this function was a fourth order polynomial, using a fourth order Taylor series will produce the same exact result. The reason is that the fifth derivative is 0 actually for this one. That's why that's the exact solution. And the remainder term, actually there is a remainder here, R4, equals, and this one, if you remember, f derivative, the next one, n plus 1, and the c value or psi value 5 factorial and h5, and this becomes 0 when we use the fifth factor. So if you remember, the third derivative was this. So if we get the fourth derivative, for example, let's say this was equivalent to minus 2.4, and the fifth derivative, this one, or 5, let's write 5. These are too much. In parentheses, that means derivative is 0. So if the fifth derivative is 0, we don't need to consider about this c value or psi value. Any values of f is 0 for the fifth derivative, and any values of the fifth derivative function is 0. That means this one is 0, which gives us R4 is 0. That means we will have an exact value for the fourth order. This is the remainder term. So fifth order derivative is 0 for a 4 order polynomial. That's why a 4 order polynomial, that's why a 4 order Taylor series gives the exact solution for the 4 order. Let me write it down. Fourth order Taylor expansion will give an exact prediction of a fourth order polynomial. We can generalize this for an nth order polynomial. An nth order Taylor expansion will give an exact solution. And with this, we showed how the Taylor expansion can be used for predicting the values of a polynomial. And with this, we finish this example.